So go to the calculating correlation coefficient in Excel. So the first spreadsheet under chapter 4. Okay, so calculating correlation coefficient, let's open that up. Okay, so what are we doing? We have a set of simple points, and I have the simple points 1, 3, 4, 5, 7. Okay, I want to go over to the side. So I'm making a new worksheet, and I've got 1, 3, 4, 5, 7. Okay. I want to see how those numbers, oh, actually I have two numbers. 1, 3, 4, 5, 7 are the X's, and 5, 9, 7, 1, 13 are my Y's. Last time we worked with the Pearson's fathers and sons. I highlight both sets of those data, and we said we can look at how they relate to each other if I insert a scatter diagram. So I highlighted them, I inserted a scatter diagram, and looking at that, except for this weird point down here, it looks like I have a pretty nice line going right across the top. We said we could see the correlation by simply going to add trend line, and I display the equation, display r squared. We didn't get much further than this, but I can see that my line has a slope of 0.8 and a y-intercept of 3.8. Okay, so that's pretty clear. Four, right? So my number, I hope I don't lose y'all at home because it just said my internet connection is unstable. My number is either going to be a 0.4 or a negative 0.4 because either of those I can square. All you need to do in your head is if the line goes up, the correlation coefficient is positive. So all I did, it's got to use flip down. All I did, right click on a point and add trend line. And then over on the side, I'd click the bottom two things, display equation on the chart, display r squared on the chart. So if you click the graph, did you get it? Right click on a point. You can even right click. You have to right click on a point. So just right click on a point. Is it not doing it? So I add the trend line, and then I pick the bottom two ones. Okay. So looking at that, if I need a value for R is the correlation coefficient, right? Then R would be either 0.4 or negative 0.4, because squaring both of them gives me a 0.16. If the line slopes up, and it does because it's a positive slope, it's positive 0.4. If it slopes down, it's negative 0.4. Okay, so that's what we did last time. We know, or the book will tell us eventually, that 16% of the variation in Y is accounted for by the variation in X. Okay. We can also find the correlation coefficient very quickly by just saying, and if I wanted to be one of the richest people in the world and I wanted a program that was easy to understand, what might I have people start typing to find the correlation coefficient? Yeah, so just start typing COR, and there it is, Correl, tab. It says array 1, comma, array 2. So it says pick the X's, comma, pick the Y's. Enter. So that also gave me the same answer, 0.4, and in this case, it's 0.4 exactly. Okay, that's R squared. This is R. Just to let you know that there's another option out there. Who invented the correlation coefficient? First name Carl. Pearson. I can also type Pearson. Pick the X's, comma, pick the Y's. Same answer, exactly. So those functions are exactly the same. It's just they're two things that do the same thing. Okay, so that is a, yes?
How did you get 0.4R?
So I either use Correl or Pearson. I highlight the X's, comma, I highlight the Y's. So that's the way that we'll normally do it. But we need to understand what's happening, right? This is very much like a standard deviation in 2 dimensions instead of a standard deviation with just x's. Okay, so we're going to go back to the first thing in there. And this is why we don't do things by hand. Okay, if we wanted the formula for R, it's n, which is number of things, and we have 1, 2, 3, 4, 5 ordered pairs, right? 1, 5, 3, 9, 4, 7, 5, 1, 7, 13. So I have n. So 5 times the sum of the x's. Well, if I have x and I add them up, I get 20. 4 and 4 is 8, and 5 is 13, and 7 is 20. So 5 times is not even the sum of the x's, it's the sum of x's times y. So I multiply x times y, and then I sum those up, and I get 156. So 5 times 156 minus the sum of the x's, which is 20, times the sum of the y's, which is 35. Your head should be hurting now. Time over the square root of n, which is 5, times the sum of x squared. So I came over here and I squared the x's and added those up, which is 100, minus the sum of x, which is 20. I squared 20 and I got 400, times the square root of n, which is 5, times the sum of y squared. So take each y, square it, add those up, minus the sum of y, which is add up all the y's, I get 35, and then square that number. If you do all that, you get 0.4. Yay. Okay. That's a horrible way to compute the correlation coefficient. I have another way that I like a lot better. Okay. And it's called using standard units. And we'll use standard units a lot throughout this course. Okay. And just before I move on there, this was the sum of x times y. I said 1 times 5, and then I added them all up. Is there another way to get this box without doing any work? Can I get here without having to do anything first?
Yes.
Yes, how?
Sum product.
Right, so if I type sum product, that says multiply these x's times these y's, and then jump straight to the answer. So that helps a lot. Is there a way that I could have gotten the 100 for x squared without having to do any work? Sum squared. So square each x individually, 1, 9, 16, 25, 49, add them up. Is there a way that I could have gotten this 325 without doing any work? Yeah, sum squares y. So that says 25, 81, 49, 1, and 169, and I get 325. So that is actually a lot easier. You can plug everything in down here without having to do any manual computations. And one reason I show you this way, this is the book's formula for it, but some of the homework will ask you to compute sum of x squared versus sum of x squared. And the difference between this first term, sum of x squared, that's the sum of squares. This one is the sum of x. After you've added up all the x values, then you square that sum. So that's the difference there.
How did you do 100 again?
So 100 was just the sum of the squares.
How did you do 156 again?
So same thing, it's the sum of the, sum product. So it's x times y, and the sum of x times y. So it says multiply them and then add up those things. So sum product, take the things in column 1, or the blue things, and then multiply them by the red things. So 1 times 5 plus 3 times 9 plus 4 times 7 plus 5 times 1. So you can always find it the long way, but it's really nice. Like that was a lot of work that we just blew away with 3 formulas. And again, I'm hoping it'll help because I'll post the video I'll post after class 2, so you can always come back and look. Okay, so coming back here, I'm going to start over, and this looks a little easier. I have my x's and my y's. I want to find the mean and the standard deviation. So that's simple. I can say equal to the average of these things and the sample standard deviation is what I want. So the standard deviation, I think I want the sample standard deviation. I want the population standard deviation. Okay, so the mean is the average of these things, the standard deviation of the population of that. Now what's really cool, if I just drag this to the right, it fills those in. Because it said the average of those and the standard deviation of those. Okay, now, to find the standard units, what standard units mean, it is, let me fix that. How many standard deviations away from the mean is this number? So standard units will convert to, we'll call them z-scores in the next chapter. Okay, if you've had stats before, it's a z-score. But how many standard deviations away from the mean am I? So 1 is 3 away from the average of x, right? Or better yet, let's start with this one. 4 is how far away from the average of x? 0. So it would be 0 standard deviations away. 1 is 3 standard deviations away, right? And is 1 positive or negative? Is 1 above or below the mean? Below. Okay, so it's a -3, all right? And then 3 is how many standard deviations? You might have said I didn't hear it. Standard deviation is 2, so how many standard deviations is the number 3? 1.5, right? So I'm 1.5 standard deviations away from the mean. All I need to do is say in standard units, it is equal to 1 minus the mean divided by the standard deviation. So how far away am I from the mean? And how does that compare in terms of a standard deviation? So I should get minus 1.5. Before I drag it down and get an error, do I keep wanting these two things to drop down 1, 1, 1, 1, 1? No. So I'm going to lock my mean and my standard deviation. So the only thing that I want to be a relative reference is the B2 column. So when I drag this down, this number changes, but it keeps saying how far away from the mean am I divided by the standard deviation. So if y'all are all on my spreadsheet, it would be the same for everybody. Equals parentheses B2 minus $B $7 parentheses divided by $B $8. Okay. Now I can drag that down. And it says I am here I'm half a standard deviation below the mean. Well, 3 is 1 away from the mean. It's below, and -1 compared to 2 is -1/2. That was on the mean, so it was 0 away. This was 1 above the mean, so it's positive. 5 is 1 more than 4, and 1 over 2. And this was 3 over the mean, so it's a positive 1 over 5. We're going to do the same thing with the y column now. So 5 is 2 below the mean. 5 is 2 under 7. 2 is a half of 4. So it's going to be -0.5. So I'm going to take each number. I'm going to go here, minus. I'm going to click on the mean. I'm going to divide by the standard deviation. I don't want the mean or the standard deviation to move. I can drag that down. Just for kicks, if you add up everything under standard units, I have to move y'all to the side. What is the sum? down here? 0. And if I add everything up here, the sum is 0. So it's a good check. Almost done. I'm going to multiply the standard unit. So I say this times this, standard units in x times standard units in y. I'll drag that down. And then the average of those numbers is correlation coefficient.
How did you, for the standard units, is it always like when you're doing the x and y, it's always, like is it always minus in the middle?
Yes. So you take the original value, so the x value, and you subtract away the mean. So how far away is that from the mean? Yes.
How did you get the top one of the 0.05?
I just multiplied. So it was the product of the standard units in x times the standard units in y. Is that still a lot of work? Sort of. I'm lazy. I think it's a lot of work. Does anybody remember Freddie Madrid? Yes? So Freddie was our old student body president. Freddie sat in the first day one day in class and he said, Dr. Lawton, why don't you use the function standardize? I never knew what that was. Okay. Standardize, it says click on the x value, comma, and it tells me click on the mean, comma, click on the standard deviation. When I drag it down, the mean's not going to move, so I'll put it in dollar signs. The standard deviation's not going to move. Same thing. So that's a formula that does what we just did. Anytime you find yourself doing something complex in Excel, there's often a shortcut. And so Freddie Madrid, I like to give him credit every time. Freddie found that equals standardize. I put in my x value, and I lock it on the mean, and I lock it on the standard deviation. And it does all that for me, so I don't have to remember which one comes first. Is there a negative, anything else? Yeah.
I keep getting 1.3 on it, but I'm not
Okay, say, I don't know.
Okay, so hold on. So in the x value? Okay. All right, so tell me what you're typing.
I just restarted with the standardized one and then equal standardized parentheses, and then I have the one, there's a difference.
Okay, so 1.
Yeah, and then I have 1, comma, 4, comma, 2.
And you get,
Yeah, and it's giving me 1.3.
so something funky's going on. Read these down here just to make sure something's different.
And like the check work too, like if you sum them up, it still adds up to 0.
You've got 1, 3, 4, 5, 7, 4, 2. 1, 3, 4, 5, 7, 4, 2. And then, so read it out. Are you using standardized or are you using standardized?
I did like the original.
Okay, so let's go both ways. So standardized B2, B7, B8.
I didn't like the rest of it.
It's okay. So Audrey, did you use standard deviation dot P down here?
I didn't even check, so that might be what it is.
That's it.
No, I just did the regular, I didn't even do simple or population.
Okay, so don't like that. I'm glad you said that. So people always go back to this. Don't ever use that one because you don't really know which one you're getting. So use stdev.s or stdev.p, but in this case, you want to use .p. Say that again.
You showed a shortcut, but that page is one.
Yes. So you want to just do standardize, and then it prompts me down underneath the value, comma, and then it highlights the mean, comma, and then it highlights the standard deviation. Done. Whoa. There. Okay.
Hey, we're supposed to do which one, the P or the X?
The P. For this one, it's the population.
Okay. I think I did something else. I gotta get that number now. It's probably this name.
Okay, so just tell me what you've got down here under SD.
It says 4, I think. I mean, it does say 4, but I must have done something wrong.
You might.
I have the first standard deviation plus the new standard deviation.
Which would double it, so that'll fix it. Okay, so the idea of standard units is we're trying to figure out the correlation between the x's and the y's. So we've got two axes going on, whereas before in standard deviation we just had one list of numbers. Now we're comparing two. So that's why we take the relative distance from the mean for the x's and the relative distance from the mean and y's. And I'm saying relative because we kind of normalized it by dividing it by the standard deviation. Then we put those together by multiplying, and then we average those out. So that's what finds that for us. Okay. Honest to goodness, that's not how I do it. I like you to know that those kind of things, what's happening with the correlation coefficient is that we are looking at our number of standard deviations away from each unit. Nobody ever finds it that way. In reality, we all go in and say, Correl, the first array, the second array, done, no mistakes. But standard units will come back into play a lot in chapter 5 or 6, maybe it's chapter 6. So I like to bring them up here so they're not something you've never heard of before. And
The product, when you did the standard deviation on the other side, was it just the sum of the product of the standard units?
It was the average.
The average?
Yeah, the average of the product. So I think the book has you go find one or two of these by hand. But reality, like even if it says, because some of them it'll say, find the sum of xy, find the sum of x squared, find the sum of y squared. You know, you can find those quickly using sum of squares, sum product. But in the end, I would say equals Correl to find the correlation coefficient, or equals Pearson. The more steps you do by hand, the more prone you are to make an error. And that's why kind of in the real world, we try not to do anything by hand. We like to understand the concept, but we try not to do any individual calculations by hand because we're more likely to make mistakes. And in stats, you're often dealing with 10,000 pieces of data. So you really don't want to be typing all those in. You want an instrument to collect those numbers for you, and then you want to have a computer do that for you. Okay. So that was R. If I was going to compute R squared, how would I find R squared? Think like 7th grade. Here's R, I want to find R squared. What do? Square it, right? So just take that and square it, and you're good. What you do not want to do is say equals 0.4 squared, because what's happened is you don't know if that goes out to 17,000 decimal places and it never repeats itself. It could be 0.413964, blah, blah, blah. And when you square it, you're taking the rounded version. So never just do that. Always click on the cell and then square it. And then you're good. In this case, it was an actual 0.4, but it could go on and on and on. I don't know if I've given you a note before, but notice when I click over this, a note pops up. That's pretty cool, I think. You often don't want to have to write a bunch of stuff out to the side on your Excel sheet. So you can right-click, and they've added a new one. There's notes and comments. I think this one was a note. Yeah. And so it pops in usually the user initials for the person, and then you can put a note in here. So that's very helpful when you are sharing information across a team. Hey, this number for the total assets in the third quarter looks wrong. Draw your attention to it. Okay. So I want to look just a little bit at other things about the correlation coefficient. Here, so we did all this with the graph, and the graph is a really useful thing. Suppose I wanted to find the slope and intercept of the line for the regression equation. Do I need to do any work if I'm satisfied with this number of decimals? What is the line for the regression equation? Correlation. It's staring at you. There's only one equation of a line on the page. Yeah. Y equals 0.8x plus 3.8. So the slope is 0.8 and the y-intercept is 3.8. Is the point 0, comma 3.8. Okay, so I've got my line, but it may be that I need my line to be a whole lot more precise than what the graph gives me. And so there's a very easy way to find all this. If I needed everything that I could possibly use here, so maybe I want to say I want r squared, I want to find the slope, and I want to find the y-intercept. Okay. R is easy. That was just Carell. The x's, comma, y's. R squared is just equal to square that. Bill wants to be rich, so what's he going to call the equation for the formula to find the slope? Slope. Now, you got to be real careful here. It says slope, and what does it say first? What's the first thing that goes into it? Known y's. So I've got to put my y's first, and then my x's. So pay attention to what's underneath it. Slope, known y's, comma, known x's. I get 0.8. Same thing the graph did. What might you use for the intercept? Intercept. Known y's. It tells me which one to pick first. Known x's. So what it's doing is it's putting the dependent variable first. We're saying y depends on the value of x. The height of the father is the determinant of the height of the son, is what we're kind of going at in the math term, not in a causation term. Done. So my line would be y equals 0.8x plus 3.8. If I wanted to predict y when x equals 1.5, I would just plug in 1.5 for x. I would say 0.8 times 1.5 plus 3.8. Yes? So all I did was say intercept, and then the trick was it tells me put the y's first. That's kind of the only place people make a mistake, is they put the x's first. So always watch, y's first, and then x. And that is really the point. I always tell this to my calc students all the time. I hear my calculus teacher screaming at me. The y-intercept is really the point x is 0, y is 3.8, but b would be 3.8. Right. Notice the difference here. It doesn't say known y's, known x's. It says array 1, array 2. In that case, it doesn't matter what order I go in. I could put the y's first or the x's first. It wouldn't matter. But it does matter on this slope and intercept. Yes? I clicked on equals, click on the one above, and then square it.
So initially, this is just another way to.
So equals, I clicked on 0.4 and then caret.
Yeah, I get that part. I'm talking about for the R. When I'm doing my correlation, I'm getting different numbers. I'm trying to figure out.
Oh, here. Yeah. So you want to do Carell or Pearson. Make sure you highlight the whole first column, put a comma, and then highlight the whole second column. Okay. That's the whole chapter. That's everything that could happen. I want to give you a couple different scenarios where we look at pictures. So if I say x and y And I'm just going to put in, I'm going to substitute some different values. So you can just watch me for a second. Don't try to repeat what I'm doing. Oops. What's cool about that line? Whoa, if you could see it. It's a really nice line, right? All the dots line up onto the regression line. What's the slope of the regression line? 1. What's the y-intercept? Y equals mx plus b. It's really y equals x plus 0, right? So it intercepts at 0, 0. What's the correlation coefficient? I have two choices for my correlation coefficient. It would either be what or what? 1 or negative 1. And so if this correlation coefficient was a negative 1, that would mean the line goes down. It doesn't. So it's got to be 1. So if I plug it in, I get 1. So r squared is 1, which means 100% of the change in y can be attributed to the change in x. Everything lines up. That's true because what can you look at in my original number set? How do x and y relate to each other? They're the same, right? So yeah, 100% of y is related to x because they're the same. Same thing if I said this was equal to 3 times that. The correlation coefficient is still 1. My line changes, the slope's a little steeper, but it's a perfect alignment because, yeah, x perfectly predicts y. So it's a correlation coefficient of 1, and r squared 100% does. If I change it just a little bit more, so I'm going to say now y is negative 3 times that. What happened to my line? Yeah, it flipped upside down because I now have a negative slope. It's still a perfect prediction. R squared still 1, but if I plug in and get r, so if I go down here and I say r is equal to Corel of the known x's and the known y's, I get a negative 1. So that's where you need to be careful. Just because r squared's 1, you can have a positive or a negative square root. If the line is going up, it's a positive r. If the line's going down, it's a negative r. All your functions will give you the right answers. Just be careful on that. Okay, now I'm going to be a little bit more tricky. Don't try to do this. A little crazy. Does x perfectly predict y? No. I can see a line, but it's not real great. It's fine. Actually, it's really not that bad. R squared says 79% of the change in y can be attributed to or correlated with the change in x. Kind of cool. What I did to give you a quick set of numbers, I said multiply that by a random number between 20 and 60. If I redid it all, which it keeps recomputing, I get a different one, and this time 68%. So you see, as the numbers look more cloud-like, the correlation coefficient gets really small. So in Pearson, we said that 25% of the height of the sun can be correlated with or attributed to the height of the father. Right? Correlated would be what we end up with there. But 25% of the variation in the height of the sun is related to the variation in the height of the father. So here it's pretty good, 68% is in there. Things you need to be careful about. You can correlate a lot of really cool stuff, and there's a website on like random correlations, and it shows that the number of deaths by strangulation in your bed sheets is an almost perfect correlation every year to the pounds per capita of cheese consumed by people in the United States. Weird.
Oh, number of deaths by drowning in pool correlates with the number of Nicolas Cage films every year.
Right. So stuff like that. Like what? Just because it's correlated doesn't have anything to do with the fact that one causes the other. So I used to give that in the homework, like interpret this graph for me. And people would give me these really complex things about, well, people who tend to eat more cheese might be overweight, and then the overweight might cause you to strangle in your bed sheets. But none of your data says that the people who strangled had anything, like they might be lactose intolerant. They might not eat cheese, right? So it's just random. Yes. Okay, so really good question. What's the difference between r squared and r? R is always going to be a number between -1 and 1. So a perfect correlation means that you're at either end. So when we had equals 5 times that. So this has an r value of 1. It's a perfect correlation, and it means that as x increases, y increases, and they perfectly align. If I changed r to the other extreme, so this has an r value of -1. So that's the, like r can never be 4. It's always between -1 and 1. The -1 and 1 both mean perfect alignment. -1 r means it's going down, and they're perfectly aligned. As I get closer and closer, so do this. Everybody pick a number for me between 1 and 100. Have your number picked. Somebody else give me a number. So 43? Wait, no, it's the same person. You're not random anymore. Somebody else give me a random number you'd already picked.
17.
Somebody else, a random number you'd already picked.
2.
Now, r is negative, like that graph's a mess, right? Because once one of you starts spouting off your number, if somebody else changes, then it's not random anymore. But like when I say everybody pick one, theoretically we're random. One has very little to do with each other, right? So my r value, they do go down. The trend line goes down a little bit, but it's pretty close to 0, okay? So r being 0 means like we threw darts at the board. There ain't nothing, one has nothing to do with the other. And here r squared says only 3% of the variation in y has anything to do with the variation in x. So they're directly related, but one we use to explain a little bit more. But always, r can never be less than -1 or more than 1. R squared would always be between 0 and 100. Yeah. And then the key thing too, the one last 1 minute thing I have, hopefully you've heard along the way, correlation does not imply causation, right? Just because two things have a high rate of correlation, like you and I wear a raincoat on the same days, we don't have anything to do with each other. I did not cause you to wear a raincoat. We both woke up and we heard the rain on the roof, right? So we can be highly correlated, but neither one of us caused the other's behavior. That's a huge trouble when people write up scientific studies in the paper. They'll miss that really important point.
So just remember that correlation is not causation.
Right, correlation is not causation.
Thank you.
Okay, take care.
Have a good one.
Bye-bye.
Okay.